Hello, welcome to this video. My name is Minzhang. I would like to give an introduction for the paper we recently published. The topic is about an investigation on early evolution of soot using large AD simulation. And this work is guided by Jens Walter in DTU. The most important phenomenon during the early stage of soot evolution is soot spec. So we need to know what is a soot spec. As you can see from this picture, it shows the experiment set up from ECN where the n-dodecane fuel is injected through the inject nozzle to a constant volume chamber. The conditions in the chamber are engine-like conditions. After ignition, we can see the soot spec as the soot increase rapidly. So this is the first characteristic for the soot spec. Then the soot mass reach a peak and then decrease to form a spec. So this is the second characteristic. In this picture, we also can see some blue and red lines. These are some results from others' simulation. It's very clear that they cannot predict the soot spec very well. So in our study, the research goal is to predict the soot spec and understand the mechanism behind this soot spec. First, we need to do the modal validation. And for the top picture, we show the distribution of soot mass, the soot volume fraction at different time instants. So we can see the distribution in the simulation show a good agreement with the experiment data. For the bottom picture, it shows the temporal evolution of total soot mass in the domain. And as we can see, the present LES model is able to predict the soot spec both in the 15 and 21% O2 cases. Here we did a comparison of lift of lane and soot mass between LES, Uranus, in-place LES, and experiment. For the lift of lane, we can see that the lift of lane in the LES case are shorter than that for the Uranus case. And if we look at the right picture, we can see the soot spec in both the LES and the in-place LES cases. But we cannot see that in the Uranus cases. So when we compare the LES and the in-place LES cases, we can know that the LES subgrid model doesn't play a very important role in the successful prediction of soot spec. But when we compare the Uranus and the LES result, we can know that the Uranus turbulence closure is the main reason to the failed prediction in the soot spec. in a recent paper where they speculated that the steep gradient of mixed fraction in the height is the main reason to the formation of a soot speck. So we did a check on that. And we can see a steep gradient of mixed fraction can be observed in both the Uranus and the LES cases. If we look carefully on these pictures, we can see that the spray combustion region is rather wider but penetrates to a short distance actually in the LES case. This tells us that the mixing process in the LES is slower. And we know this slower mixing process in the LES case will result in a large favorable region for soot formation. But we still need to further confirm this point. Here we did a discrete PDF of equivalence ratio. For the top picture, we show the soot volume fraction as a function of equivalence ratio. For the bottom pictures, we show the PDF as a function of equivalence ratio for both LES and Uranus cases. As we can see, and the discrete PDF of phi is higher in the LES case than that in the Uranus cases before 0.8 millisecond after start of injection. So you can see the black bar is higher than red bar before 0.8 millisecond. This tells us there are more favorable region for soot formation in the LES case. And if we look at 1 millisecond, we can see that the values of discrete PDF in the Uranus case are greater than those in the LES case when the equivalence ratio is larger than 1.8. So we can see the soot volume fraction during this region is higher it's higher in the Uranus cases. In this slide, we check the temperature evolution of discrete PDF of equivalence ratio. As you can see, in the LES case, we can see that the discrete PDF of phi at the favorable phi region, larger than 1.5. For soot formation, increase from 0.6 millisecond to 0.8 millisecond, and then decreases. So you can see the red line at 0.8 millisecond is on top of other lines. This tell us the soot speck is formed in the LES case. Then if we look at the Uranus case, we can see the discrete PDF of phi as the favorable region for soot formation and continues to increase until to 2.2 milliseconds. So we only can see the soot increase gradually and then reach the steady state in the Uranus case. Then we come to the conclusion. First, the LES is able to capture the soot speck, but the Uranus cannot. And for the second point, and the fiber region in the LES case is larger than that in the Uranus case during the early time. So we can see a very rapid increase in the Uranus case during the early time. The fiber region for soot formation in the LES case increase and then decrease to reach a steady state. But this fiber region for soot formation in the LES case continue to increase. So we can see a spike in the LES, but not in the Uranus case. If you are interested in this work, please refer to the full paper online. Okay. And thanks for watching this video.